My name is Lucas. I'm working at the Scala team at TypeSafe with the other three guys. So we are four: Adrian, Jason, me, and Greg. A lot of the work that we, is collaboration. So I will, from time to time, say who is doing what. Just, it's also a nice piece of insight for everybody to see what people are working on. All right. So Scala 2.12 on one slide. This is certainly not everything, but it's everything that fitted on a slide. So there are two main topics. One is we move to Java 8. So the backend will target Java 8 and only Java 8. So the bytecode will not run on any previous version of Java. There's a few things we can do thanks to that. So we can take advantage of new bytecode, new library features of the VM. And here are three topics that I want to highlight. So the first one is interoperability for functions. So functions in Scala and functions in Java, from Java 8, they will be compatible in certain ways. I will talk about this in detail. Second topic is we can make use of default methods in Scala for compiling traits. I will also go a bit into detail there. Another topic that Rex is working on is interoperability with the streams library from Java, and this one I will skip in my presentation, but I'm sure you'll have a chance to catch up some other time on this topic. The second big topic of Scala 2.12 is the new optimizer. So the goal of the new optimizer is to be more reliable, more better configurable, have better command line options to say what you want, better error messages if things go wrong, and in general have fewer bugs as well. So one thing that we already fixed, for example, a very long-standing bug is that you can inline methods that are defined in traits. So if you have a final method that is defined in a trait, you can inline that. Is one of these things that was never possible with the current optimizer. Just out of curiosity, who is using -optimize in Scala? Okay, John. Not so many people. It's what it's more or less. It's more or less what I expected. So the Scala standard distribution is built with -optimize, but we know that most people are not using -optimize right now, and I hope this will change in the future. So the agenda for the talk is more or less what you just saw on the last slide: interoperability between Java and Scala functions, and then how we can make use of default methods. And for the new backend, so what's the architecture of the new backend? What is different compared to the current one? And and then a longer section about the new optimizer. What can it do, and what are the limitations? Where do we want to go in the future? Okay, functions, interoperability of Java and Scala functions. There are two levels. One is source code and one is bytecode, right? So on the source code level, what you want is to be able to basically have the Lambda syntax when you write Scala code, but you are calling a Java API, then you want to have it exactly the same as if you were using Java. So that's the first example here. You're creating a thread and you're just passing a Lambda with the code that is executed on the thread. And this is already possible actually in Scala 2.11. We'll see it in more detail. The second direction, the opposite direction, is if you have a piece of Java code and you are calling into a Scala library, then you want to be able to use Java's Lambda syntax to pass a function to the Scala library. And we'll go in detail how these two things can work. On the bytecode level, well, it's maybe not exactly interop, but basically what we want to do is emit the same bytecode for creating functions, for creating closure objects, do the same thing as Java does. All right, so first example, if you are writing Scala code and you want to use a Java API, and then you want to be able to have, this nice Lambda syntax whenever the Java API has a function in the API. So that's the same example we had before. Now the first thing is to notice that Java 8, it doesn't have any function type per se. Instead, every type that has one single, actually every interface that has one single abstract method. So that's this thing here called SAM, single abstract method. So every interface that has only one abstract method can be instantiated with the Lambda syntax. So this is Java code, right? You have an interface with one method. We have the class thread, the thread constructor, which takes a runnable. And you can create a new thread just by passing a lambda, okay? So what will happen here is that various pieces of magic will basically create a runnable instance with the run method having this body here. Okay? Now, our goal is to have the same syntax in Scala. Okay? So if you write Scala code, you want to be able to do the same thing. And this is in fact already implemented in Scala 2.11.6, so you can try it out, but it's behind the experimental flag. Okay? Now the opposite direction. This is again a piece of Java code, so now what I'm talking about, oh wait, sorry. No, this is still the same direction, sorry. This is still using a Java API when writing Scala code, all right? So this is just a bigger example. So the most famous Java API that makes heavy use of lambdas is the streams API that was introduced in Java 8. And this is just one example. So you take a stream, you call filter, and you pass it a lambda here in this case. In the second example, you pass it a point-free method. So you just pass it the reference to a method, which is then expanded also to a lambda, and so this is the typical kind of code that you would write when using the Java Stream API in Java, okay? Now if you do the same thing in Scala, again Scala 2.11.6 with experimental, you can do exactly the same thing and it just works. So you take a stream and you call filter, you call map, you call sorted for each, and you get the result, okay? So this is already implemented. Adrian did all of the heavy work there. It was actually not that straightforward. There were a few interactions with type inference that had to be sorted out. All right, now we go to the opposite direction. Now we're talking about, you write an API in Scala, and you have some users that want to consume it from Java code, okay? So here, the example is Scala collection. Okay, you take some Scala collection. In Java, you call for each, and you pass it a Java lambda. Now, what's the condition for this thing to work? Well, in Scala, every function, so for each method takes a function 1, okay? Maybe, yeah, function 1. All right, so in Scala, in order for this to work, the function trait defined in Scala has to have one single abstract method. Otherwise, the JVM cannot instantiate the lambda, right? So I will go into detail while this doesn't work in Scala 2.11 right now. So in Scala 2.11, the function traits, they have more than one abstract method. And I will show you later, but basically in Scala 2.12 this will work. In Scala 2.11 you can have it work if there's a reason for you to, if you're writing Java code and for some reason you are consuming a Scala 2.11 library, then there's this compatibility layer implemented by JSON, which you can use and which provides you with a little wrapper function, okay? And you can pass your lambda into that wrapper, and then from there to the for each, and then the things work. All right, so that was the source code level. Interoperability, both directions between lambdas. Now we're talking about bytecode. So let's start off by looking at an example how the Scala compiler in 2.11, how the Scala compiler translates lambdas. So in this example, we have a collection we call reduce, and we pass it a function with 2 arguments. What the Scala compiler generates is an anonymous class, which extends function 2, and the code, the body of the method, is in the apply method of the function, okay? And then it just passes this anonymous function, a new instance of that anonymous functions to the reduce method. I'm glossing over a few glorious details here. I'm sure Vlad is going to be upset because I'm not talking about primitive types, and we have specialization in function 2, so I'm skipping over these things a little bit just to make it easier to understand. All right, so that was Scala. What happens in Java 8 if you create a lambda? This is a complete example. So I defined an interface, int function. Okay, so it takes an int, it takes 2 ints as parameter, and it returns an int, single abstract method. And we have a test. Well, we have a reduce function which takes such a a function as argument, and then we call it with a lambda. What does the Java 8 compiler generate? Well, it's not exactly the same as in Scala, in fact. So what is generated is a private static method that contains the body of the lambda. So the body of the lambda is x plus y, and this private static method, it has two parameters, just like the lambda, and it implements the body. And then the invocation of reduce, it needs to pass an object, a function object, all right? So where does this function object come from? Well, basically there's some magic sauce, which I don't go into detail now, but basically there are some special instructions that tell the VM, you need to create a closure object that takes this thing as the body, so this is the method body, okay? And this is what you need to implement. So you need to implement IIA function.apply, okay? The way this is done is well, maybe you heard about it, invoke dynamic and lambda meta factory. So again, I won't go into details, that's a different talk, it's a complicated topic. But the point here is that what we would like to do in Scala 2.12 is do exactly the same thing, all right? So now what's the condition? So what do we need to do in order to do the same thing? So first of all, we need to be able to create this method that contains the lambda body, all right? And it turns out we already have that. So in Scala 2.11, there's a command line option which is called -Ydelambdafy method, all right? And if you turn that on, then the lambdas are created slightly differently. This has been implemented by James Eyre. So the same example as we had before with the Ydelambdafy method, what you get is an anonymous, a static function, okay, which takes exactly the same parameters as the closure and has the closure body in there. And then the lambda class that the Scala compiler generated simply delegates to that function, that method that was generated before. So basically we extracted the method body from the lambda into a private function. And this class here is complete boilerplate, right? So this is, there's no code in there which is specific to the lambda that you're actually writing. And now to go from there to the scheme that Java 8 is using seems relatively straightforward. Of course, again, Jason will not agree. There's plenty of small details that need to be taken care of. But if you look from above, from a far enough distance, then what we do is generate this method with Ydelambdafy method, and then use the same calling convention as Java 8. So we use invoke dynamic and lambda meta factory. Yes.
Java 8 has some restrictions with regards to closures, specifically you cannot capture variables.
Right, you cannot capture locals.
If we go through this generation, we won't have the same problem?
No, you get the same functionality. Yeah. All right, so what's the advantage of using that scheme in Scala? Well, first obvious thing is that we don't need to generate any class files for lambdas anymore. So the result is that your jar files become smaller. You don't have one unknown fun class anymore for each function that you write. Another advantage that will hopefully pay off more in the future is that by using the standard scheme, we tell the JVM more about our code. So basically the JVM will know, okay, this thing here, that's a lambda, and we hope that in the future the JVM will possibly implement better optimizations for code that uses lambda, and if you use their scheme, then we'll automatically be able to profit. And in general, it's just it goes in the same category. So just be a good citizen on the JVM and do what they expect you to do. Okay, so that was interoperability for functions, and one thing that I skipped a little bit over was this. How do we do function one? How does it become a single abstract method? And that's the next topic. So we're talking about default methods. There's a question.
Yes, during Vlad's talk, it was mentioned that Scala sort of came late in the game to the Java 8 lambda implementation, and it caused a whole bunch of issues and limitations. So I was wondering if that's something that was worked around or has ramifications on user code.
No, on user code there's not any impact that you would see. there's just more work that needs to be done by Jason. You can talk to him. Yeah, there's a few small things that yeah, a few things that need to be done. I think one of the main problems I remember is that in Scala you have unit, which is also an object, whereas in Java void is not an object. So the Lambda meta factory does some automatic boxing and unboxing, and that doesn't really work because the Java this Lambda meta factory doesn't know how to box our our unit into a unit value and back, because that doesn't exist for Java. So small things like that. Okay, so default methods. So we talked about function 1, right? So function 1, if you look at the source code in Scala, it has one single abstract method, apply, all right? And then it has a number of methods that are not abstract, that have a method body, that are concrete. So there's compose, there's and then, there's also toString. And how is that compiled? So here we are talking about 2.11 and target JVM 6. How is that compiled? So basically for every trait that has some non-abstract members, we generate two classes. The first one is an interface, which contains exactly the interface as the source code, obviously. And the second one is what you call the implementation class, and it contains static methods for every concrete member of the original interface. Okay, and you have the method body here. And the important thing to notice is, well, because we are on Java 6, is that all the methods in F1 in the interface have to be abstract. They cannot be anybody, obviously. So what happens if you implement a function 1, okay, you create a subtype of function 1, then the Scala compiler will automatically create forwarders for all the concrete methods to the implementation class, right? But the problem that we have with Java interop, with Java 8 interop, is that this interface is not a single abstract method interface. It has multiple abstract methods. So if you want to create a function 1 from Java, you cannot use Lambda syntax, okay? So how are we going to fix this? Well, obviously we can make use of default methods. So, maybe just for those. So a default method in Java 8 is basically allows you to have a concrete implementation of an interface member. Okay. Yeah. So in 2.11 we cannot do much because it targets 1.6. So the bytecode is not compatible. In Scala 2.12. We have a number of options. So the blunt option would be to basically write the Scala.function n traits in Java code. And then we don't have to do any work in the Scala compiler to be able to emit this new bytecode. So we can just, but this is very problematic because another thing is, the main problem there is that the Scala compiler adds metadata to all classes that it emits. And then if you consume, if you use function n from Scala, then you get nice error messages with the precise types and stuff. And if you write those in Java, then yeah, there might be a number of drawbacks. Another option, if we want to be a bit less lazy, but still lazy, is we can just, special case function n in our JVM backend and say, okay, this is function n. I will just add a few default methods for some of its members. Or the probably best option that we plan to explore if there's enough resources available is to extend the Scala compiler to be able to make proper use of default methods when compiling traits. Yeah, so assuming we do that, so assuming we have all the support in the new in the 2.12 compiler to make use of default methods, then we basically can write much better Java APIs from within Scala, because all the interfaces that have a single abstract method, they become SAM types in bytecode. Another advantage of using default methods in Scala is that there's a few cases where it helps for binary compatibility. So we did a few experiments already, but we haven't started implementing this thing in the compiler yet, okay? But we did a few experiments how a translation scheme could look like, how we could make use of default methods when compiling traits. And one of the experiments mentioned here is STUDY, so the research compiler being developed at DPFL, and they make use default methods for compiling traits. Okay. So still talking about default methods for compiling traits, there are basically two options we can do in the current compiler. Okay, so there's a simple solution which would be to basically add a forwarder to the interface that is generated by the compiler. So in the case of function 1, it would mean that apply remains abstract, but the compose method simply becomes a default method and gets a forwarder to the existing method in the implementation class. The advantage here is that this is relatively simple to implement. Our other option would be, of course, to skip, creating this implementation class altogether and move all the code that trait members have directly into the default methods. The problem here is that it touches a lot of stages in the compilation pipeline. So these implementation classes are created super early in the compiler, and then there's the mixin phase which changes things around again, and it might be a bit of too much of a change to do in one release. We are not exactly sure yet where things are going there. Good. So that was the first part of my talk. Let me see. Oh, good. So for the rest, let's talk about the new backend. So the current backend in Scala 2.11 has more or less this architecture. It's a bit, okay. So what happens is you get abstract syntax trees. That's the program representation that we start with, that the compiler works with in general. And then there's several phases that transform that thing to bytecode, so to class files. The first thing is a phase called GenIcode, which transforms the trees into a new intermediate representation, which is called Icode. Icode is relatively close to the Java, it's a close representation of the Java bytecode already. One thing to notice is that the Icode data structures, they point to symbols and types that are defined in the Scala symbol table. Okay. Then the current optimizer, so the 2.11 optimizer, it works on this Icode, so the Inliner would modify this code here. Then there's a next phase which is called GenASM. ASM is an open source library for creating Java class files. And so there's a GenASM phase which creates the ASM trees, which is their representation of Java bytecode, and then we write that thing to the class file. So everything that's in red here is, these things about, basically the red parts are the parts of the backend that we have to maintain ourselves, right? And the reason the pipeline looks like this is rather historical. So in the beginning, we had a different library to write class files, and Icode was generated with the intent to be able to write an optimizer. But now that we are using the ASM library, it turns out that this is actually not a bad target for writing an optimizer. So in the new backend, which is already, it's actually already available in Scala 2.11 under a flag. So in this new backend, we skip this Icode, okay? Instead, we have a new phase which is called GenBCode, which directly transforms Scala syntax trees into the ASM bytecode representation. There's a new kind of data structure here, which is called B types, backend types. And these B types, they are completely independent of the symbol table, all right? So once you're past GenBCode, the program representation doesn't depend anymore on the earlier stages of the compiler. Okay, and then you have a new inliner, new optimizer, that's the thing I'm working on, and the bytecode writer, which is the same as before. So the GenBCode backend was implemented by Miguel Garcia at EPFL. All right. So what's the advantage? Well, there are fewer components to maintain. One big advantage is that this new representation is thread safe, so there's a potential to run, for example, to do class file serialization in parallel or run some local optimizations in parallel. This is what is not the case if for programs that depend on the Scala symbol table, because the symbol table is inherently non-thread safe. And the ASM framework is also a good platform to implement optimizations. So there are some built-in tools for code analysis, and also the representation is just easier to work with. There are fewer invariants, so things like that. Okay, for the rest of the talk, let's look into the optimizer. So the optimizer on GenBCode is originally prototyped by Miguel. So he has a website where he explains his project and shows some great results, some numbers, and also runs already some stuff in parallel. And we are now working on implementing more and more of that into our compiler. So it's very much a work in progress. We have some local optimizations available in 2.11.6. The Inliner will be in the next release, 2.11.7, so that's basically ready. And in the future, yeah, we will work more on eliminating unnecessary allocations like functions, closures that are not used, or boxed values that can be unboxed, things like that. And a big topic will be finding good heuristics. I will go into these things in more detail. So we have a sub-agenda for the rest of the talk. So first question, actually, why do we need an optimizer? Features and roadmap of the optimizer. What are the limitations? And then a bit of dreaming about the future. What could we do if we had more time, let's say. So, why do we need an optimizer? So the Java virtual machine is a very, very powerful runtime that optimizes the bytecode that it executes, and it has runtime statistics available, so it can look at the code and count how often is something executed, what types flow into a certain part of the program, and it can make use of all of that information to optimize the code. So why would we even bother? Well, it turns out that there's a number of patterns that the Scala compiler generates and that Scala programmers use often that we know the JVM doesn't optimize very well. And the goal of the optimizer in the Scala compiler is really to help out the JVM, so to produce code that can run fast. And the goal is not to try to do something that the JVM does anyway. So we will let the JVM do its work because it does it very well. So what kind of patterns are those? I will give you two examples, and we have to go a little bit into detail here. So first one is related to virtual method calls. So here we have a class a range class with the for each method. So you pass a function to for each, and then in a while loop, okay, the for each method will call the function that you passed. So this method call here is a virtual call. That means the code that gets executed, it depends on the type of the value that flows to this point. So in the first example, we execute the method foo. In the second example, bar. So what happens here is that the JVM has to look at runtime at the type of the receiver and then decide, okay, where is the code to execute? So he has to do a lookup. And this lookup is slow, all right? And it prevents inlining. Now what the JVM does, it gathers statistics, all right? So while running the code, the JVM will continuously check what is the type of F, okay? And if it turns out after a few hundred iterations the type of F was always the same, then most likely the VM will decide to optimize for this case and start inlining. So it will start inlining the body of this apply method, okay? So yeah, I won't go into all details, but basically the just-in-time compiler will, let's assume we are not in this example, let's assume there's only a single function that is ever passed into for each, then it will optimize for that case, and the VM, so the compiled code will have a guard, so it will have a type check, and then in case at some point something unexpected happens and a different function goes there, it will do a de-optimization and roll back. Okay. So now, So we said this method lookup is very slow, all right? And what we really want is to be able, since we are calling this f.apply in a while loop, we want to be able for the VM to inline this call, okay? And if we have a large number of function types that reach this place, then the VM cannot inline because it just cannot do the right decision, okay? And then this loop will be slow forever. And this problem is very well known. It's called, well, I think one of the most famous articles about this is by Cliff Click. It's called, he names it the inlining problem. The article is 2011. There's also a recent article by Alexei Shipilev where he talks about method dispatch in the JVM in general, and also, of course, about this problem in particular. And those are both very good reads. Okay, so what happens here? We assume that we have a large number of function types that reach this point. In that case, so what you say is that this call site is megamorphic, so there's many types that reach this place. Because it's megamorphic, the VM cannot inline it, all right? So what could we do? How could we fix that problem? Well, what would help in this case is if we inline the for each method. So if you go one step further out and you inline the for each method, it creates a copy of the body, right? So the entire body of for each is copied into the call site. And then you have the call site f.apply in that copy becomes monomorphic. There's always the same type, because at each call of for each, you will create a new copy of the body, right? So that's what we should do. The problem is the VM doesn't do that. I will show you some benchmarks on the next slide. It just simply doesn't do it. They don't do this multi-step tracing of method calls. And the call site to for each is typically not hot, not called that often. Therefore, things are slow and not inline. So here's here's a benchmark. So if you have one or two types passed to for each only, so here we're talking globally, like you have an entire program, right? You call range.forEach, and over the life cycle of the program, there's only one or two functions that are ever passed into for each. Then in that case, it manages to optimize it. So it will inline one or both of these methods, do a type test, and things are fast. If the call site becomes megamorphic, then you have a 10x slowdown. You can do a simple benchmark. And in the last example, I basically created the code which manually inlines the for each method into the call site. So we have 6 different functions, so 6 different calls of for each, but we inline them, and in the first case we call foo, in the second case bar. So it's still, we pass many functions there, but the performance is back to normal. And so that's one of the examples that the Scala compiler can optimize. Second example, because it's so nice, we use range.forEach again. And in this case, the closure that is passed to for each modifies a local variable. Now, how is that even possible? Because the local variable here is not on the same stack frame as the function that is being executed. So what happens in this case is that the Scala compiler will transform the local variable into a so-called ref, which is basically a box, a simple object containing the local. Okay, and then the function f, instead of, because it cannot modify the local variable, it will modify the intref, which is captured, right? So that's what happens. Now, before going into details, when you do a benchmark of that thing, you notice that it's slow. Okay, and why is it slow? Well, I mean, let's say it's not obvious. I mean, it's pretty obvious that it's very likely that the intref is the reason, because a read and write to a local variable is obviously faster than going through an object and chasing pointers. But what is not so obvious is what do we need to do to improve the situation. Okay? So let's look at it in detail. This is the code again. So the code creates an intref, creates the closure, and passes the closure to for each. Now, if we, as a first step, you inline for each, so the code of for each, and we inline also the body of the function. Okay? What we end up with is we create the intref, we create the closure, which is actually not used anymore. Then we have the body of for each and the body of the lambda. Okay? Turns out this is still slow, okay? And now at this point it's pretty obvious. I mean, what makes this code slow is the fact that you go and read and write a local variable, if you want, through the heap, which is not ideal. And it turns out there's an optimization in Java virtual machine that is supposed to catch this case. So it's supposed to realize, oh, we create a local object and we modify its field, okay? But that object actually is only within that piece of code, so it could optimize it. But that optimization is called escape and it fails in this case. And the reason it fails is because we create this closure, okay? So now, in the next step, we just eliminate this line, okay? We eliminate the closure allocation. The code is still exactly the same, and now it's fast. Okay? And finally, for comparison, we have the same code again. We have an intref, so a local object that we read and write, and we compare the speed of that with basically the perfect code where you have one local variable and a while loop. So it turns out the performance of the last two cases is almost the same, okay? So the VM manages to optimize this thing very well, okay? So what's the story here? So what I'm trying to point out basically is that it's not easy to figure out what should we optimize in the Scala compiler and what not. What is the VM able to do, and where does the VM fail, and what are the reasons, right? And the message here is that we need to be basically very benchmark driven. We need to be careful, like, not do too much work, because if you inline too many things, your methods get big and then things slow down again. And so that's the takeaway message from this thing. So we need to do something to improve certain cases that we know, but we have to be careful and benchmark driven. Okay, so as I already mentioned, so in 2.11.6, the optimizer, it has some local optimization and like dead code elimination, and it will have more of these things. Even though these are the things that typically the Java virtual machine would do well, it's still worthwhile to implement some of those in the compiler, because just to make the bytecode look pretty, because it's very hard to work with bytecode that is hard to understand, and these are simple to implement, so there's no big cost to them. The inliner is basically ready, so it will be in the next release, and our future plans, well, as I already mentioned, so we will work on closure elimination and also other unnecessary objects, and again, lots of testing, lots of benchmarks, and tuning heuristics. So a few details about the inliner. How does it work? So the inliner, it's really a transformation on the bytecode level. So the inliner doesn't require any information from the compiler front end. Everything that it requires, all the information that it requires, is serialized into the bytecode, right? And the inliner has a very explicit call graph representation, and that will be helpful for people, if you want to try out and see what kind of heuristics you can come up with. Then you can just, go through the call graph and find your call sites that you would like to inline, things like that. One area where it improves over the current inliner of the 2.11 compiler is error reporting. So you get much more precise error messages that tell you why something couldn't be inlined, what the reasons are, what the instructions are problematic, and things like that. And finally, we invest a lot of time in testing. So community build is an extremely helpful tool that we have nowadays. Greg talked about it earlier today. Well, just as an example, one thing we recently did with the inliner is added a thing called insane mode, where basically the inliner would try to inline as much as it can. Every method that can be statically resolved, it would try to inline. And the result here is that we can bootstrap the compiler, so everything works. But maybe just, again, talking about heuristics. So if you inline everything you can, okay, and you get a new Scala compiler where everything is inlined, the problem is that this compiler runs 2 times slower than a normal compiler. And the reason is you get these huge method bodies that the JVM will almost never optimize anymore because they are just too big. So again, we have to be very careful when choosing what to optimize and what not. Okay, so collaboration. So I recently started being a bit more open about what we are doing, what the plans are. I mean, it's not about openness, but it's just about putting it down somewhere. So I created this GitHub repository, Scala Opt, where there's an issue tracker which contains a lot of plans and to-dos and things that we want to work on. There's small things like, we need to rewrite this method because it's just slow the way it's done right now, and there's of course bigger things. So if you want to keep track of what's going on, then that's the best place to go and to have a look. You can obviously file issues if you're trying it out and you find bugs, then feel free to log an issue. And just if you want to chat with us, we recently created this Gitter channel, and it's picking up slowly. So it's a good opportunity if you want to talk to us. People are online. Okay, well, running out of time, but this point I want to make. So there's one very, the story so far sounded pretty good, I would say, but there's one very, very unfortunate but inherent limitation to the inliner that you have to keep in mind when you use it. So when you inline from a library that is on your class path, so you write a program and you depend on some code, some bytecode, okay, and you inline from that bytecode, then basically the way the optimizer is written right now, we don't give you any guarantees if you change the library. So that means if you inline from a specific library at compile time, you need to have exactly the same jar file on the class path at runtime. Okay? Because there are things, there are methods that, for example, are public, whereas in source compatibility they would still be private and things like that. So basically, we don't have any guarantees right now if you switch between versions and you have the optimizer enabled. And that is very problematic for people that write a library, right? So if you write a library, then you inline from your dependency, then everybody that uses your library has to use that dependency with the exact same version, okay? So here's a visualization. You have some library, okay? And this library, while being compiled, it inlined from a dependency of version 1, okay? Then somebody else, okay, writes some completely different library, inlines from the same dependency, but version 2, okay, not the same version. Now what happens? If you're a user and you want to depend on both of these things, okay, then you're supposed to have, well, basically both or neither of those two things on your class path, so you get the conflict. Okay? So that's a really harsh limitation that we have here. So as a library author, right, basically right now you can only inline from within the same project, but you cannot inline from other libraries that you have on your class path. So that includes obviously the Scala standard library. So if you're using range.forEach, for example, in your code, it will be slow. So we are looking into this. Maybe we can come up with a set of rules, or we can come up with an inliner mode that would say, okay, inline only against public API that is supposed to not change. But this is a future work, and we haven't done that right now yet. Okay, what can you do? Well, as I said, you need to have the same version. Well, one thing that you can do to work around this problem is compile everything from source, right? There are people doing that. There are tools out there that are becoming more and more popular that do exactly that. So that's, if performance is that critical and it turns out this new optimizer is so useful for you, then that might be an option. Another option, okay, so that's more of an outlook into a distant future, is a whole program optimizer, right? So that's basically a way we could solve this binary compatibility issue. The idea there is that the optimizer doesn't run when compiling a library, but instead, when you compile a library, you just create the bytecode, not optimized at all, okay? And then everybody who creates a final application, this person takes the entire class path, and then it runs a global optimization at link time over the entire thing and creates a new jar file, something like that, okay? This is obviously related to what Martin talked about in his keynote. So he was talking about this tasty AST interchange format, which could be an obvious choice for implementing such an optimizer. But I believe it would also be possible even to do it simply on the bytecode without having this new interchange format. This approach has been successfully proven to work in Scala.js. So Scala.js does exactly this. When you compile a library, then it creates this intermediate representation. And all libraries are published in that way, and then only when compiling the final program, the link time optimizer will take all these intermediate representation and put everything into a single JavaScript file and inline basically across the entire project and run the optimizer. And so this approach, depending on your resources, which doesn't seem to be a problem anymore these days, it seems to be very successful. So what can you do in a global optimizer? Of course, you have much more liberty. So when the optimizer that I talked about so far in the Scala backend, we cannot, for example, just remove a public method because it's unused, or remove a class because it's not unused. We don't know. The world is open, okay? You're writing a program, and then somebody else will depend on your library. If you know that the program that you're compiling and optimizing, everything is in there, then you can start being much more aggressive. So you can look through the entire type hierarchy and say, this type is never used, so I just throw out a class file. And then this gives you more and more information where things disappear, and then more and more call sites become statically resolvable, and you can do a lot more optimizations that way. Okay? So as I said, this is not work in progress even, this is just talking about the future. There's multiple ways we could implement such a thing, so we can work with just class files, or we can work with the tasty representation. And it's also not that this will solve it will solve many problems, but also introduce a few new ones. So one obvious thing that becomes problematic with the whole program optimizer is support for reflection, because if you start removing things that are public but unused, or you start changing the program around a lot, then runtime reflection will just not work in that same way anymore. And this is a known problem to other projects, and there's no simple solution to this thing. So again, there might be multiple modes where you say, okay, I don't use reflection, then you can profit more, things like that. All right. 2 minutes over. That was it. Thank you for your attention. Yes.
So with respect,
There's also, it's okay. More for the video.
So with respect to the boundaries, the cross-library compiler optimization boundaries, you've mentioned some of the challenges and some of the sort of long-term possible solutions to that. I'm a little concerned that you did not mention what the strategy is that you're actually employing short-term for the optimizations in 12.7 and 12.
Right. So you have command line flags. So you can, when you compile a project, you can say, I only want to run the optimizer within my code, or I also want to run it on existing bytecode.
So what would be the default then?
The default would probably be the save option, yeah.
Yeah, okay, terrific. That's what I wanted to hear, thank you.
Well, at the beginning of the presentation, you asked who here used the optimize flag. And I just wanted to say that I know about the flag, and the reason I never use it is because I'm afraid that it's going to make my compilation even slower. It's going to take even more time.
Right.
So can you please comment on how the new backend, and in particular the new optimizer, are going to affect compilation time?
Right. So, one thing to mention is that running the optimizer is not something you're probably doing in development mode. It's typically you would run the optimizer only when you compile your entire project for production. So you would do it once. Maybe we should have better support for these things in the build tools, so that it's easy to when you create the final distribution that the optimizer gets enabled and not otherwise. In terms of performance, so one example I mentioned was this insane mode where you try to inline as much as possible. And what we observed there, I didn't work on making it like I didn't go into details and started profiling or anything. So that's really the baseline performance that we have right now. When you compile the Scala library without optimizer, it takes like 50 seconds, my machine. And with this insane mode enable, which does a lot of work, like really it tries to inline every call site that it finds, it took something like 2 minutes. So it's, of course, not something you would want to do again in development mode, but like a 2x slowdown is acceptable, I would say. Oh, in practice it would be less, yeah.
One other question is, you're saying about the JK8, and we know that Scala 2.12 is going to be JK8 only. But Monday, during the keynote, I had the impression, when Martin was talking about tasty, I had the impression that you are reconsidering keeping support for JDK6, so because of taste. So is that something that you are considering, or no? It's close to you?
For 2.12 you are pretty much set on JDK8. Yes.
Okay. Thank you.
Okay. Any other questions? No. Okay. Thank you.